The big focus today is going to be showing you the difference between solving an equation and proving something, because it's really easy to mix those things up. Most of the time, what we deal with in math class is proving something that we call a conditional equation. And that's just an equation that's only true some of the time. So like when I say solve sine of x equals 0, you go through and you tell me where that's true. What values make that true? And that's when we get like x equals 0 and x equals pi. What we're going to focus on today is not solving an equation in that sense, but we're going to prove some identities, prove how some things are equal to each other. So an identity is true all the time, no matter what. This is only true for certain values of x. And so this is an identity that we know is true. No matter what value you plug in for x, that's a true statement. And so you're going to see these equations today, but you got to think about them in terms of identities and not normal equations. And so that's kind of the big focus of the day. And just like all the other stuff we've been doing, it takes some time to kind of get the process down. And the more you practice, the more you realize things and you see things. And I have lots of tricks for you today. Maybe not tricks, tips on advice if you get stuck on a problem on what you should do. And so we're going to kind of do one together so I can show you the idea, and then I'm going to give you some tips, and then we're going to do a few more. And then hopefully we're at school tomorrow to do some more. It is. Before spring break? No, they're adding it on to the end of the year.
So why is that?
I better not record this. Oh my goodness, let's just not think about it. Okay, this is in your book, and it's up to you if you want to write these down, and I'll totally wait for you if you do. But then the next page, I have some tips in my own words. But this is what the book says you should be doing. The proof begins with an expression on one side of an identity. So I want to kind of talk you through this. Logan, you got to focus today. If you want to. Well, that's not good, because this is kind of really important, and it's very new, okay? You're going to see something on each side of an equal sign. You have to pick one side to work with, so that's why it says the proof begins with the expression on one side. So you can either choose to start with the right side or the left side, it doesn't matter, but you got to pick one side. Here's what's nice about proofs. It's telling you what you should equal. Like, you know how on the worksheet yesterday, you're like, is this the right answer? I got 1, or I got cosine, or I got -1. Is that right? The nice thing about a proof is if we say we're going to work with this side, we know what it's supposed to equal. It's supposed to equal this when we're done. So that's why the second step, it says the proof ends with the expression on the other side, because when you're done, you should get the same thing on both sides. Step 3 is the one I want to emphasize a lot. Because you know what's supposed to happen, think back to those lovely geometry proofs. You knew what we were supposed to prove, and most of the time you just made up stuff in the middle, and then at the end you would write the last step and write proven, which is not an appropriate proof step, but people did anyway. The part in between is what I'm grading. The proof in between consists of showing a sequence of expressions, each one easily seen to be equivalent to its preceding expression, which means I have to be able to tell what identities you're using and what work you're doing to get from one step to the other. And if it seems like you just jump straight to the answer, you're not going to get your credit on that. Depends on how much work you show, or if it's the right work. No, if you just write this, and then you write that they're equal to each other, and nothing in between is remotely correct, you're getting no credit. No, has to be right jazz. So on one of my steps I'm going to give you in a minute, My advice is always start with the side that looks like there's more stuff to do, the side that you could simplify more. But really, it doesn't matter. You could pick either side here and start doing things and try to turn it into the other side. That's the point of this. This is not a normal equation, which means at no point should you ever be taking something over here and adding or multiplying or subtracting or dividing it over here. This is just to tell you what you're supposed to equal at the end. You follow me on that? So for me, I'm going to pick this side just because I like this side. And I always feel like if they give me addition, maybe I could get a common denominator and I could turn it into multiplication. Like I feel like there's more to do with addition than there is to do with multiplication. So I picked the more complicated side to work with. And then I just want to say, what could I do to simplify this? So this is the problem they give you. They give you this. It says, prove this. So you have to decide, am I going to prove this, turn this into this, or am I going to turn this into this? And for me, I'm going to turn this side into this side. So I'm going to ask myself, what could I rewrite tangent and cotangent as that maybe somewhere eventually would turn into secant and cosecant? So what are my options? What could I write tangent as? Yes, sine over cosine or 1 over cotangent are my two options. I think sine over cosine is a good option because this is also something to do with sine and cosine, right? So you want to kind of think, this is my end result that I'm looking at. So I'm going to rewrite tangent as sine of x over cosine of x. And then could I rewrite cotangent as cosine of x over sine of x? And then as you go along, rewrite that other side. Like this is kind of like, this is what it's supposed to equal eventually. Keep stuff in order. This is a proof, so we're kind of just like working it vertically here. And it's going to take a few steps. Some proofs are really simple. Some proofs are a little bit longer to do. But now that we do this, you have an idea of what we could do next to make that simpler? For me, again, these are kind of strategies. You see how this is addition? Do I have addition over here? Which means if I'm trying to turn this into this, I have to somehow make this not addition anymore. So could I get a common denominator in hopes that that's going to become one big fraction that maybe I would get rid of the addition? So that's another thing to look for. If I have addition over here and I don't have it over here, a common denominator is usually a good way that maybe we can get rid of that. So my common denominator, do you agree that that's just going to be cosine of x times sine of x? This times this. And on the top, I got to multiply by the one that's not there. So on this one, I have to multiply by sine of x. So I would get sine squared of x. And on this side, I would have to multiply by cosine of x. And I would get cosine squared x. Again, remember that a proof is the steps in between really matter. So I always say, if you're not sure if you should show a step, if you think, should I show this step or should I skip to this step? Show the step. Like it's always better to show more work than to skip a step and for me to say, how did you get here? And you say, come on, you knew that was true. So if you're not sure, show the step. What about now? Do you see anything over here we could do? Sine squared plus cosine squared, that equals 1, right? Those are three identities that you should know, which means if you know this equals 1, you can just replace it with 1. That's okay to do because we should know that. So I'm going to rewrite that as 1 over cosine of x times sine of x equals secant of x times cosecant of x. And again, even though people really get scared by the word proof, what do I like about proofs is I know what I'm trying to do. Like I kind of did this, very similar to what we've been doing. But now look at this and look at what we're trying to get and think about what I could do, or if there is something I could do to make this turn into this. If I have 1 over cosine of x, what is that the same as? And if I have 1 over sine of x, that's cosecant, right? Like I'm allowed to flip those up. Remember I told you if you ever have a trig function in the bottom, you should move it up. So do you agree that this is the same as this? So I'm just going to rewrite it. 1 over cosine of x is secant of x. 1 over sine of x is cosecant of x. And once I get that those are equal to each other, that is proven. So I like to put a little check mark. Or you could be really cool mathematician and put like 3 little dots. I don't know. People put it next to the proofs. Proven. That's what I think it means. I like check marks. You don't have to put anything, really. That's the idea of a proof. How do you feel about that? Excited, right? The hard part is getting started, and so that's why I have a bunch of tips for you. And so I definitely recommend writing these down. These are not tips that are in your book. These are just tips that I feel are good tips. So when you get stuck, these are the tips that you should be looking at. And this is, I kind of said this already, but you're only going to work with one side. Like you're never going to multiply both sides by 3 or divide both sides by sine or square both sides because you're just trying to prove that they're equal to each other. And again, I say work with the side that's more complicated because there's more stuff to do. Some people like to work with one side for a little bit and then work back with the other side, and they're not doing it at the same time, and that works as well. We can look at one of those in a minute if you want. But as long as you're not doing something to both sides of an equation, you're not breaking any rules on this. So it's just like they're giving you the answer. That's the difference between these problems and what we did before. And so every one of these we do today, I'm going to ask you, which side do you want to work with? And there's not always a clear-cut answer. Sometimes they both look terrible, and it doesn't matter which side you start with, which is why it's so much fun to grade these. Because everyone can do them differently. Just like what we've been doing, try those strategies. Look for factoring if there's a common term you can factor out, or if it's a trinomial. If you see fractions that are added, you probably could get a common denominator. Maybe square a binomial, and we'll look at one like that. Or if you could get the denominator to be just one thing, no addition or subtraction, that's what monomial means. But those are basically the same strategies that we did on the worksheet. You're going to apply those same strategies to this stuff. Which is why I threw that extra day for a worksheet in here. What else is super important? Know your identities. Those Pythagorean identities are going to show up a lot. The basic identities, that tangent is sine over cosine. The reciprocal identities. You've got to know those basic identities when you're doing these. What else do I enjoy about these proofs is step number 4. Look at what you're trying to get. If you have tangent in your answer that you're trying to get, your goal would be at some point, how could I make this turn into tangent? And by remember which pairs match up, that's those Pythagorean identities. Remember that sine squared and cosine squared go together. Cotangent squared and cosecant squared go together. Like those ones that cancel each other out. We're almost done. Algebra, big important thing that we've been working on a lot in 5.1. But remember that you can square two things, a plus b times a minus b will always give you a squared minus b squared. Or if you see a perfect square minus a perfect square, that you can factor it out. I kind of put these in order of what I think are the tricks you should do. Like, these are the things you should be going with. Number 6, some people like to think of this as their first step, and I don't think that this is a good idea. But if you can't figure something out, one idea is to always convert everything in terms of be kind of your last resort for the most part, unless you already see a sine and cosine in it. Sometimes people start with number 6, and they create this big giant proof that's not nearly that complicated. So 6 is a good last resort, should not be your first step. And don't leave these blank. Try something, because sometimes if you just start doing some stuff, you're going to get something to cancel out that you didn't even see at the beginning. It's definitely are worth a decent amount of points on the test. Leaving them blank is never a good thing. On your homework, you got to try them, because you're not going to get this process down if you just wait for me to do them every time. That's not going to help you either. So we're going to start with some basic ones. Maybe not too bad today. Tomorrow they get a little worse, but not too bad. Also, you're going to notice they're going to use lots of different Greek letters for these proofs. Do the best you can with them. Some people like to change everything to x or theta. I'm not really opposed to that, but don't be afraid to draw some nice Greek letters. Alright? So that's your tips when you get stuck on your homework. Important. Alright, so let's do it. Again, remember I need to see some work here. So make sure that you give me a little bit of work here. Some of these are not going to be very long proofs. Some of them will be longer. Whatever you want. I think it's okay to write a Y for next. I'm going to use lots of different letters. I just said that, didn't I? You got left one. Which side are we going to work with on this one? Definitely this side, right? Like, could we turn one into something? We could, but this is definitely the side that has more stuff to do that we should be able to simplify to get 1 at some point. And again, there's lots of ways you could start this. It's just what you see. So, I don't know. What do you see? Secant squared y minus 1 should maybe make you think, is that a Pythagorean identity? And I'm okay if it is, that you can just substitute in what that is. So you got to know those. What is it? Secant and, which one go together? Tangent? 1 plus tangent squared equals secant squared. So notice, if you recognize that, you're going to be able to substitute in something right away, because you could subtract 1 over. So secant squared minus 1 would be just equal to tangent squared, right? Do you agree with that? If you didn't see that and you distributed there, I don't know that that's the wrong answer. You just are going to have more steps. And that's the thing. Sometimes people take 7 steps to do a proof that takes me to do 2 steps. Sometimes I do a proof in 5 steps and someone else can do it in 3 steps. And so it's just all about what you see when you do that. But I'm going to replace that with tangent squared y, because that's my Pythagorean identity. And then this is where it's a proof. So I say, show me something here to show me how you know this is true, that you're not just guessing to the right answer. Because we know where we're supposed to end up. We're supposed to end up with 1 equals 1. And maybe you're like, well, these are reciprocals of each other, right? They should just cancel out. I can just write 1 equals 1. It's a proof. Show me that extra step. So could I rewrite cotangent squared in a way that I could show that I'm going to be able to cancel those out? Yeah, could I write this as 1 over tangent squared? Or I guess I could have written it as cosine squared over sine squared and sine over cosine. That would also work as well. But this is what I mean by I need to be able to see some steps, that you're not just jumping to the end because you know that's where it's supposed to end. Everybody with me on that? So then I could say 1 equals 1. I'm done with that proof. That was only a 2-step proof. That wasn't bad. How about this one? I'm going to give you a minute to think about it before I just tell you what to do. So look at this one, and again, this is an example of one I think it doesn't matter which side you start with, because it's about the same. But remember, you're not allowed to add or subtract something to both sides, because what a lot of people want to do on this one is they want to like subtract 3 from both sides. It's not okay. You got to either turn this into this or this into this. So maybe you can look at that for a minute and see if you can think about what we could do to make those equivalent to each other. What about theta? Can you okay with theta? Why not? Wait till you see like omega on here. Somewhere. Mu. Again, maybe some thought process here as you're thinking of this. If I have tangent squared, I want to turn it into secant squared. Or if I work with this side, I have secant squared, I want to turn it into tangent squared. So in my head, I think about, do I have a way that I have something that relates tangent squared and secant squared to each other? I have that lovely Pythagorean identity, right? So, got some options here, but secant squared equals 1 plus tangent squared. If I work with this side, could I replace this with this? And then I would have at least tangent squared on both sides, and I could simplify from there. So again, it's kind of the thought process that you want to start thinking about. How could I turn this into that? So I'm going to leave this side alone on this one. And I'm going to replace secant squared, and I'm going to show my work here, with 1 plus tangent squared, and then plus 3. And if I simplify that, do you agree that I've just finished that proof? Yeah. So just that one step, knowing that Pythagorean identity, tangent squared theta plus 4 equals tangent squared theta plus 4, I've proved that. Pythagorean identity is so, so important. You could have done the same thing on this side. You could have changed tangent squared to what secant squared minus 1, and you would have got the same thing, which is why it doesn't matter which side you work with, as long as you end up with them equaling each other. Questions about that? It's pretty easy, right? Want to do a harder one? This is one like your homework, and I wanted to make sure I showed you the directions here. Because instead of saying, prove this, they're asking you, is this true or not? And so the directions here say, tell whether or not f of x equals sine of x is an identity. So they kind of just write it a different way than the normal proof. And so they give you f of x equals tangent of x over secant of x. Now this is an example of a problem that you might get that it doesn't work. On the other directions, if it says prove this identity, it will always work. That's why the work in between is so important. But this is an example where they want to know, is this true or not? Does tangent of x over secant of x, does that equal sine of x, is what they're asking you to show. And you might get to say no on that, because it might not work. If it says verify the identity, it's always going to work. So this is on your homework, so I want to make sure that I showed you this. So try that. Try to simplify tangent of x over secant of x, and see if you can get sine of x or not. tangent is sine over cosine. And so then if I leave secant in the bottom, that's 1 over cosine. And then what can you do? Yeah, dividing by a fraction is the same as flipping it up. So sine over cosine times the reciprocal, which would be cosine of x over 1. So then those cosines cancel out. And again, I'm kind of just saying, does this equal sine of x as I go? And I think it does. Sine of x equals sine of x. So I would say yes to this problem, that it does work. Something else I just want to throw out there, just as another way of writing it, pretty much the exact same steps, only I wrote this, like when I did this, I wrote it first as tangent of x times 1 over secant of x, like I just separated these two because it's for fraction and I'm allowed to do that, because that's the same as it all together. And then I pretty much did the same thing, I just didn't have to multiply by the reciprocal. So I wrote that as sine of x over cosine of x, and I can bring secant up and just made it cosine. And then I still got the same answer. So lots of ways you could do this as long as the identities are correct and your algebra is correct. Let's try one more, like a real proof. Verify this identity, that cosine of x times tangent of x plus sine of x cotangent of x equals sine of x plus cosine squared x. And again, there's lots of ways to start this, but my advice to you is, which side do you want to start with first? I would choose the left side. It definitely looks like there's more work to be done. And what do you think would be a good first step on the left side? And again, there's more than one thing to do. What? Yeah, I would probably distribute there. Distribute that cosine. And then maybe we have some other stuff to do in there. But again, show me the work here. So don't jump to the conclusion that the answer is sine of x plus cosine squared of x. So I'm going to write that as cosine of x times tangent of x plus, this is just going to be a big old cosine of x times sine of x times cotangent of x. And again, if you're getting stuck on this, look at what's on the left and what you want to have on the right. So when I look at my answer, I only have sine and cosines over here. And when I look over here, I still see a tangent and a cotangent. So I think about, if I only want sines and cosines, could I go through and rewrite tangent and cotangent in terms of sine and cosine? And I could, and then hopefully that something's going to simplify out. And so if you get stuck, that's what you should look at. What do I have? What do I want? And what identity could I use? So I'm going to rewrite all this again, but I'm going to change tangent to sine of x over cosine of x. And I'm going to change cotangent to cosine of x over sine of x. Again, see how important it is to know these identities. And then from there, you should see some simplifying that's going to happen. And hopefully, you'll either be at your answer or be close to your answer. But I could cancel out a cosine. I could cancel out a sine. And look what I have left. I have left just sine of x here. And I'm just left with cosine of x times cosine of x, which is cosine squared of x. And that's exactly what I wanted. Sine of x plus cosine squared of x. Questions about that? Some people like to change the sines and cosines at the beginning before they distribute. Again, it's okay. You still get the same answer. It's just whatever you see when you're doing this. Like, what's the hard part about this? Well, they can always throw in some other things to make it a little bit more difficult. But for the most part today, I feel like if you just use these basic strategies, you should be pretty good to go on these. And then we'll look at some harder ones. I'm sure there's some of these we'll look at tomorrow in class together, and then we'll look at some that take a little bit more work. And then 5-2 day 2 definitely has some harder proofs on it. But today, hopefully, won't be so bad. And maybe you won't have such a fear of proofs anymore, because these aren't so bad. They tell you what you want to get. Maybe even a little bit enjoyable. Maybe just for me. This is 5-2 day 1 homework. 5, 7, 10, and 12 through 33 multiples of 3.